Hi everybody. In this video we are going to start section 2 of chapter 4 and we are going to go over the addition rules of probability. But before we do that, we're going to talk a little bit about the properties of a probability measure and discuss a little set theory. And that's what this video will focus on. And then in a subsequent video, we will talk about the addition rule. The most important property of a probability is to understand that it is a positive, a non-negative number between 0 and 1. It will never be less than 0. It will never be greater than 1. It can indeed be 0 or 1. For example, the probability of a sample space will always be equal to 1. It is the certain event. And the probability of the empty set, the set with nothing in it, will always be equal to 0. It will always be the null event. And also, keep in mind that any event E is always going to be a subset of our sample space. Therefore, your probability will always be a number between 0 and 1. Now, sometimes you'll see the probability expressed as a percentage, even in some of your homework. I am sort of tolerating that. Once again, the probability is a number between 0 and 1, and is typically not a percentage. But for the purpose of this course, we will also accept percentages. Now, one of the things that you're going to be tasked to do in this section is to identify which values cannot be a probability, which brings us to example 1. As I mentioned before, the probability can never exceed 1 and never be less than 0. So accordingly, this value cannot be a probability. It's just greater than 1. It can be 0, so that's cool. It can be 1/8, that's less than 1. And 99%, that is actually as a decimal 0.99. So that would be okay as well. Next, what do we have here? Well, this one would be fine. Once again, as a decimal, this is 0.25, so that's between 0 and 1. This is a negative number. Can't be this. Okay? And of course, it can indeed be 1. Okay, so that is the first thing that we need to talk about relative to probabilities, and the first thing you'll be assessed on in your homework. Okay, this brings us to some set theory. Now, the first thing we want to talk about is this idea of a union, which is also associated with R, or not R, but or. Now, the union of two sets is a set that contains the elements in either the first set or the second set. If it is in the first set or the second set, then that element belongs in its union. And of course, it's also denoted by this symbol right here. I like to call that the cup symbol. Okay, so as an example, let A be 1, 2, and 3. Let B be 2, 4, and 6. What is the union of A and B? All those elements that are in A or in B. So that would be 1, 2. Now, even though 2's in both sets, we only include it once. 3, 4, and 6. And once again, we associate the term union with the term or. Okay? As opposed to intersections. The intersection of two sets is a set that contains the elements that are in both the first and second set. And as an example, well, let's start off with A and B again. Here we have 1, 2, and 3. B has 2, 4, and 6. The only element that is in both sets is the element 2. As a consequence, the intersection of A and B is 2. And also notice that we associate the intersection with the term and. The intersection of two sets are all those elements that are in set 1 and also in set 2. So we have union, we have intersection, we now have complement. The complement of a set E is the set of all outcomes or a set of all elements in the sample space that are not in E. The complement is typically denoted by either by a superscript C, sometimes by a bar over top, and sometimes by an apostrophe. As an example, consider the dye experiment. Now, in the dye experiment, the sample space consists of the values 1 through 6. So then let E be the elements 1 and 6. Then its complement is going to be all the elements in that sample space that are not in E. That would be 2, 3, 4, and 5. Notice that E and its complement do not share any common elements. As a consequence, the intersection of E and its complement will always be the empty set. Also notice that the union of E and its complement will be equal to the sample space, so the probability of E or its complement will be equal to the probability of its sample space, which will always be equal to 1. As an example, take a look. Here is E. The probability of E is 1/3 or 2/6. Here's E complement. Its probability is going to be 1, 2, 3, 4 divided by 6 or 2/3. Notice that the probability of E's complement is always going to be 1 minus the probability of E, or the probability of E will always be equal to 1 minus its complement. Okay? And that brings us to the complement rule for probability. As we just mentioned before, the sum of the probabilities of an event and its complement is equal to 1. And it turns out that since they are mutually exclusive, which we'll talk about in just a second, their probabilities actually add together directly. That's not always the case, which we will learn about in the addition rule. As a consequence, the probability of its complement will always be equal to 1 minus the probability of the event in question. Why is this important? Well, sometimes it's easier to find the complement and then just do 1 minus that to find the probability of an event. And we'll see an example of that, perhaps not in this video, but in a subsequent video where that's actually the case. Okay, this brings us to example 2. In example 2, which is kind of similar to your homework, which is what we're doing like this, describe the complement of the event below. Okay, and what we have here is that 80% of a person's credit card purchases are $500 or $50 or more. So its complement is going to be those credit card purchases that are not $50 or more. And remember, if you're in it's a complement, then that means you are not here. So the complement of 80% is going to be 20%. You have an entire sample space of 100%. 80% is going to be here, so then 20% has to be in its complement. Okay, for our next problem, this is also similar to your homework. Here we want to find the number of outcomes in the complement of the given event. Okay, so out of 344 high school students, that actually happens to be the size of your sample space in their senior year, 176 are right-handed. Okay, so this is E, and there happens to be 176 students. How many are going to be in the complement? Well, then the number of people in the complement is going to be equal to the number of people in the sample space minus E. Number of people in the sample space is 344. The number of sets in here is 170, or number of people in here is 176. And notice that I'm not really describing sets here, I'm describing the size of each set. And that is going to be equal to 168. That would be our answer. That is what we are looking for. And we have another question here. Okay, here in the game of craps, you roll a pair of dice and you observe the sum. If the sum is 2, you lose. What is the probability of rolling a number greater than 2? Now, it turns out that your possibilities are you can either roll the event associated with rolling a number greater than 2 is the event of rolling a 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, that is the probability of the event that we are looking for. Now, to compute this, you would need to compute the probability of getting a 3 plus the probability of getting a 4 plus the probability of getting a 5 all the way up to 12. That might seem like a daunting task, but it turns out that the complement to this event is the probability of rolling a 2. What is the probability of rolling a 2? Well, it turns out that from our previous section, we know that there are 36 total outcomes when you roll 2 die, and there's only one way to roll a 2, right? First die has to be a 1, the second die has to be a 1. So if that's the case, this is very easy to compute. We just did it. And therefore, the probability of rolling something greater than a 2 is going to be 1 minus that value, or 1 minus the probability of its complement. Okay, so that's going to be 1 minus 1 over 36, which is 536. I'm sorry, 3536, which is a fraction that cannot be reduced. Okay, and this brings us to our last thing that we need to talk about relative to set theory, and that is the idea of mutual exclusivity, or the idea of mutually exclusive sets. Now, two sets are mutually exclusive if and only if, oh, there's a mathy term for you, they have no members in common. Okay, so suppose that I have two sets A and B. If I tell you that A and B are mutually exclusive, then that means they have no members in common, okay? And their intersection is going to be the empty set because any member in A is not in B. Therefore, they have no common members. Therefore, the intersection is an empty set. If I tell you that A and B, that the intersection of A and B is equal to the empty set, that means they're mutually exclusive. Note that any event and its complement by definition are mutually exclusive, because if you're in here, you cannot be in your complement. Okay, so let's just go through a few examples for this. Let's consider ourselves a deck of playing cards. Here we go. All right, here we have the set of all clubs, and here we have the set of all diamonds. Notice that none of these elements are common. These are mutually exclusive. Their intersection would be the empty set. Pretty straightforward, huh? All right, next. Here's an example of two sets that are not mutually exclusive. Here I have a deck of playing cards. This one is the set of all clubs. This one is the set of all fours. Notice that they share a common element. There it is, 4 clubs. These are not mutually exclusive. And I believe I'm going to close out this video with one example. And here it is. You want to determine whether the events are mutually exclusive. Choosing a club or a red card out of a standard deck of cards. Now, to do these, you need to know something about playing cards. And if you don't, you're going to need to learn a little bit about them, because we use these quite often in our homework. But also in your homework, they have an example of a stack of cards. Now, one thing about clubs. All clubs are black, i.e. they are not red. So this would be a set of all the set of all clubs and the set of all red cards would be mutually exclusive. Okay, next. Choosing a club or a king out of a standard deck of cards. Well, keep in mind that both of these events have a common member. The clubs contains a king of clubs, and the set of all kings contains a king of clubs. So they share a common member. Therefore, they are not. That's a lousy O. There we go. Mutually exclusive. And that is all I have for this particular video. Stay tuned for a follow-on video where we actually will discuss the addition rule for probability. Until then, if you have any questions, please feel free to contact me. This is Bob Boyle, signing off.